Hello, I'm Vanessa.
I'm Mackenzie.
And I'm Cole.
And welcome to
The Couch Potato Lab,
where we bring science to your own homes. So today is going to be quite the chilly episode, but first we need to introduce who we have here today. So who's on my left?
All right, so my name is Mackenzie. My pronouns are she, her. And a fun fact about me today is that you might think that this is my first time going live today, but it's actually my fourth. So I started the day with a live interview, then we went live on Instagram, then live on Facebook, and now we're live here on YouTube.
That's a lot of live shows.
It is my favorite thing to do.
I love it. Me too. My name is Vanessa. My pronouns are she and her. And a fun fact about me is that this past weekend on Sunday was the first time I ever made a homemade pizza, and it was delicious. Who's on my right?
Hello, everybody. My name is Cole. My pronouns are he and him. And a fun fact about me is Vanessa does love pizza, but I love bagels. And it would make my dream come true, my childhood dream come true, if today I was just able to finally eat a bagel on today's episode of the Couch Potato Lab. Usually they tell me no bagels, but I think I might have put a good enough word in that I might be able to get a bagel in today. So here's hoping. Now, before we start, we would like to acknowledge that we are filming the Couch Potato Lab on Treaty 4 territory, which is the traditional territory of the Nehiyawak, the Nukaway, the Nakota, the Lakota, and the Dakota peoples. It's also the traditional homeland of the Métis Michif Nation.
Thank you, Cole, and I sure hope that we can get you a bagel. But before that, I think you two are looking like you have a little bit too much pent-up energy, so we can deal with that.
Okay, sure. Yeah.
Here is time for an Eyes Classic boot camp. So I have 3 exercises for the two of you.
Okay.
Again, we have to do this again?
Yeah,
Yes.
well, let's warm up.
All right,
Let's do
here
it.
we go.
Always. Okay. Our first exercise is jumping jacks. That's a classic.
Jumping jacks.
Yeah.
Okay.
Let's go in front. Let's
Sure,
go.
let's do it.
yes.
I want everybody to see my form. And
Yeah.
to prove finally that my form on jumping jacks is much better than Mackenzie's.
Yes.
Okay.
You must prove your name as Swole Cole.
Yes.
As some would say.
You got
Okay.
it. How many?
5? 5 jumping
We can do
jacks.
5.
Okay.
Here we go.
You ready?
Go ahead.
Yeah. Synchro.
1, 2, 3, 4, 5. Perfect. That was really awesome. Are you two feeling like a little bit sweaty or tired yet?
Getting there.
I'm getting
Yep.
hot,
Okay.
that's for sure.
Okay, I think the next one, you might not know what this is just off the top of your heads, but it's called jumping squats.
Jumping
Do you know
squats.
what
Jumping
a squat
squats.
is?
Well, I know like a squat is kind of like this.
Okay, and
Kinda this.
I know a jump is like this.
Yeah, so I think if we just put those two together,
Okay.
we squat and then we jump.
Okay, how
Okay.
many?
3 this time.
3.
3. Okay,
Okay.
here we go.
Here we go.
1,
2,
2.
3. Nice.
That was excellent.
Perfect.
Ooh, I'm feeling a little bit of a burn.
Any
going on
heavy
there.
breathing? Yes?
Oh yeah, like
Yeah.
actually,
A little
Yeah.
sweaty?
starting to sweat.
Well, that's okay.
Uh-oh.
We all do it.
Okay, that's totally fine. If you want to sweat any more, our next exercise is burpees.
Ooh.
Okay.
Okay.
How
Okay.
many?
Maybe 50?
50
Oh,
burpees.
fine. I'll go easy on you. 5.
5.
5.
Okay, we can do
okay.
5.
Here we go.
Okay, how do we start down here, right? And
Yeah.
then what do we do? Oh, you do a push-up? You jump. That's 2. I think we might just go to 3.
Let's
3
do
is
yeah.
good. 3
One
is
more,
good.
okay.
I'll allow it
Do I-
this
am I
time.
supposed to do
Together we did 6
Okay.
then.
Yep.
Okay.
And then we're up.
Oh, wow.
Woo.
Wow. Okay, small round of applause.
Okay,
for
thank
our
you. Yeah.
athletes.
I'm dripping in
I'm
sweat.
sweaty and I'm lightheaded.
Uh-oh.
Well, at least we're warmed up.
You're sweaty?
Yeah, I'm sweaty.
Okay.
But
Cool.
I don't know, like I'm warm, I'm sweaty, but I'm not too hot. But that's because sweat is actually called evaporative cooling. Now, do we know a little bit about evaporative cooling in this lab?
Not too much. I know evaporation is when a liquid goes to a gas, but that's about all I know.
That's right. So evaporative cooling just combines that concept. So evaporative cooling is a reduction in temperature resulting from the evaporation from one substance. So we're going to be learning a lot about that today, but that is what is happening when you sweat.
Perfect. Okay, if you get any questions throughout the show, feel free to text us at 306-570-1013, or you can tweet us using the hashtag CouchPotatoLab at EyesYouth on Twitter and also on Instagram, TikTok, Facebook, and here on YouTube. We have one quick question from Eli, and he's asking, what or who is Zeer, and why did you put that in the thumbnail? And Eli, don't worry, we are going to answer that very soon for you. It's coming a little bit later. We got to get into some things. So, keeping things cool, evaporative cooling. I feel like we've got a nice base here.
You know, Vanessa, I got to say, though, all of this working out, all of this talking about sweating, I've actually, those workouts, they were really good, and they've built up a little bit of an appetite. I'm kind of hungry, and I actually have a question for you, Vanessa.
Okay.
Do you know, what would you guess would be the biggest advancement in food technology over the course of all of human history? Think of all of the different technologies that we've developed, all of the different food-related technologies we've developed as well. To you, what do you think the most important one is?
I have to think about that hard because there's been a lot of food advancements in my lifetime even, and before that. Maybe pizza. That would have to be the biggest food advancement.
Pizza? You just made pizza on the weekend.
And it was so good. It's just, I got pizza on the brain, I guess. But Cole, am I right?
So you're going with pizza, Vanessa. Okay, I mean,
Yes.
pizza is very, very important. As we know, it's one of the 6 food groups. I'm sure it's in there somewhere. It's got a lot of good stuff going on, but it's actually not what I was thinking of.
Oh.
The food technology advancement that I was thinking of is actually a little thing that we like to call refrigeration. Refrigeration. Vanessa, do you know what refrigeration might be used for? Why we might need that?
Like in our house?
Yeah, like in our house. Why would we use refrigeration?
I always put all my food in the fridge to keep it cold, but also so that it doesn't go bad.
That's
that-
exactly right.
okay.
Yes. So the main reason that refrigeration was invented is not only to keep our food cold, but also to preserve our food. If you've ever noticed at home, if you leave some certain foods out for a long time, maybe bread or milk or fruits and vegetables, they start to go bad. They might get rotten, they might turn smelly, and you definitely can't eat them anymore. Now, part of the reason that is happening is because the temperature that those foods are sitting out at is too high, and that temperature allows tiny microorganisms, bacteria and germs to grow on that food and start to eat away at it, which we don't want because if they eat it, we can't eat it. So we had to invent something over the course of human history to keep our food a little bit cold. Now, I'll give you an example here. I've got here, and this is, what are the chances?
Oh my goodness.
Wow.
A little bit of a bagel, huh?
Dream come true.
Yeah, nature's donut, they call it. Now, bread, for example, is something that will go bad if you leave it out for too long. So if you've ever had you buy a loaf of bread, you might notice that after a while, if you're keeping it outside on the counter or something like that, it might, there are 2 things might happen. It might get hard, first of all. So like, for instance, this bread right here, it's solid. It's like it broke in half. Okay, it cracked in half. It's pretty solid. This was bread that we just had sitting out on the counter for a long period of time. Now, you can see how it cracked and how it's super, super solid because it wasn't refrigerated. And also, another thing that might happen eventually, if we give enough time, is the bread will start to grow some mold, okay? And again, that is a part of the process of decomposing of this bread because we didn't have it refrigerated. Now, the bread probably hasn't decomposed or grown mold yet just because certain products have a lot of what we call preservatives in them. And those preservatives are designed to help food last longer. They don't always work, and eventually nature will run its course and the food will decompose. But if we were to take that piece of bread and instead keep it in the refrigerator like we did this bagel,
Delicious.
still delicious. And you know why? Is because we had this bagel in the refrigerator, and it could be just as old as that loaf of bread, but because it was kept at a cooler temperature, it didn't allow any of those microorganisms to grow and decompose the food. So bread is one example of a food that would benefit from the technology of refrigeration, but I think Mackenzie knows another food that might benefit from that.
Yeah, that's right, Cole. So just because we refrigerate something, it doesn't necessarily mean that it's going to stay good forever. It might still go bad and it might still spoil, but putting it in the refrigerator just helps to slow down that process of making it, ferment or go bad or mold, things like that. Now, last night I was feeling pretty good. I had some energy left, and I thought, I should clean my room. And the main motivation behind cleaning my room was that it didn't smell great. Like, every time I walked in, it just smelled funky. And I started cleaning, and I realized that last week I had a meeting in the morning, and I had my cereal, I had my milk in my cereal, and I accidentally forgot to throw my milk out to bring my milk back upstairs, and turns out something pretty funky happened there. Now, it turned into a solid, and it definitely rotted, and that was disgusting. But what was interesting to me is that when I went upstairs to have my breakfast today, that same jug of milk that I kept in the fridge was still perfectly fine. And that has to do with the refrigeration process. So by keeping that milk outside at room temperature in my room, it went bad. But by keeping it in that fridge, it kept it nice and cold, and it slowed down that spoiling process so that it was still great for me to have this morning. So same milk, but it was kept at 2 different temperatures, and that just has to do with food preservation. So it just slows down that rate of spoiling, because eventually if I leave that milk in there and I don't use it, it is eventually going to go bad, but it will go bad a lot slower.
Wow, thank you, Mackenzie. That's really awesome, and I'm glad that you were able to still have milk left over and it didn't all go bad. Lots of refrigeration things going on. It's really excellent. Cole, do you have anything else?
Well, I just want to add that there isn't just one type of refrigeration. Now, when we talk about refrigeration, you're probably thinking, well, I've got a big old fridge at home you might have in your kitchen, and it might have a freezer too, and that's a whole another deal. That keeps things at a much lower temperature. But there's actually lots of different types of refrigeration. We talked about refrigeration being one of the greatest technological advancements in food preservation, and it truly, truly is. And it's across cultures, across different parts of the world. So up next, what we're going to do is we're going to look at a couple of different methods of refrigeration. So the refrigerator that you have in your house, maybe that you call a refrigerator, that's just one type of refrigerator. And it's one of the more modern ones, actually, and really, really fancy compared to some other ones. But there's lots of other methods of refrigeration that work just as well. And like I was saying, these have been invented all across the world through a long period of time. Some were invented a long time ago, some were a lot more recent. And the first one is called a root cellar, and that's Mackenzie. She's going to talk about that.
Yeah, so root cellars, you can see them here on this screen. And they were used a lot quite a few years ago before what we know as a refrigerator was even invented. So the principles behind these refrigerators are the same. The main goal here was to keep the food cool and to keep it preserved so that we could, at the end of the fall, we could harvest all of our food and then we could use it and it would last throughout that whole winter. So the way the root cellar works is typically they're in the ground or like in a basement or something, and they focus on 2 main things. So number 1, we want to make sure that that cellar stays cool. We want it to stay nice and cool, not too cold and not too hot. And another thing is that we want it to be very humid, so have really high humidity. We're going to touch on humidity a little bit later, but in the root cellar, the reason we want it to stay so humid is that means there's a lot of moisture in the air. And when there's not a lot of moisture in the air is constantly looking for other places to replace that moisture. So if we had food in there, then the air would be sucking out the moisture from all of our vegetables and fruits and things like that. And we want to keep that in our fruits and vegetables so that they stay good. So if you keep a really high humidity that's nice and cool, it doesn't pull that moisture out of our food and it keeps it good for longer. So typically this was used a lot back in the day with things like fruits and vegetables. So they would harvest the garden. They might can some of it, but some of it they would keep for like fresh produce as well. And they would put it in this cool and humid place. And it was typically underground because it's easier to maintain those conditions there. And one really great thing about these root cellars is that they don't require energy. So we're not having to plug something into the wall or things like that. It just has to do with the environment. So that's why we put them underground or in dark basements, things like that. Now, the one thing that's not great about them is that they do take up quite a bit of space, and they're not very practical for like urban areas, so places like cities and towns, because we don't really have places in those areas where we can dig underground and build a cellar like this, and a lot of our basements aren't designed for cellars like that as well. So throughout time, we've come up with new ways to preserve our food. Now, that one might be new for you, Vanessa. I'm not sure if you've heard of that one, but you must know of some type of refrigeration.
I do. I have never heard of a root cellar before. I feel like I've seen pictures of them. I just never put 2 and 2 together, so it's really awesome to learn all about that. But I do know about the modern refrigerator. I have experience with this one. It's in my house. You know it. You'll love it. It's perfect. The modern refrigerator, before we can talk about how it works, we need to understand 2 important concepts, which is evaporation and condensation. Evaporation, like Mackenzie mentioned earlier, is when a liquid goes to a gas. So it changes states and suddenly it's not a liquid anymore, it's a gas. Condensation is the other way. It's when a gas goes to a liquid. When you are when something is evaporating, it takes heat with it. For example, when you are at the lake or at the beach and you go in the water and then you come out of the water, you might feel a little bit cold. That's because the water on your skin is evaporating and it takes some of your body heat with it, unfortunately, and then you're not as warm. So that's why you're a little bit cold. With refrigerators, we have special stuff that helps the evaporation move along. So the refrigerant is a liquid that goes in the top of the refrigerator. It comes through, it enters at the top, and when it goes in, it experiences a sudden drop in pressure, which makes it turn into a gas quicker. And when it turns into a gas, it takes the heat that's in the refrigerator along with it. So then your food isn't going to be getting hot, because the heat is going to be leaving with the evaporation. Where does this refrigerant go, though? It can't just do that forever. It needs to be getting its pressure drop and being turned into gas. Like, the liquid can't just come from anywhere, and it doesn't. It goes back into the refrigerator. It becomes a cycle. So the refrigerant goes down to the bottom, and this makes it hot. It gets compressed, and it becomes hot. Once it's really hot, because when heat is all together, it wants to spread out. It doesn't like to be hot in one place. It wants to spread out. So it travels up really slowly through these pipes, up to the back to the top of the refrigerator like that, and it's able to release its heat to the surroundings. So the heat from your refrigerator that would be in your refrigerator goes into your house, and there's no heat in your fridge. Thank goodness, because what would we do? And then once it gets cooled off as it goes and releases all the heat, and then it's liquid again, and it's ready to re-enter the cycle at the top of the fridge. So we're very lucky to have refrigerators. I think we have one more.
Yes, we do, Vanessa. And it's really funny because all of this talk about refrigerators, bringing back so many great memories. I remember my Meemaw had a root cellar. I went digging for treasure in there once, got lost. But I did make it out, and I also have gotten stuck in a modern day refrigerator too, trying to dig for some delicious cream cheese that was at the back to put on a bagel, of course. But I'll tell you one method of refrigeration that you can't get stuck in. Or if you could, then please let me know. I would love to see a picture of that. And that's called a Zeer pot. Now, we had a question earlier about what's in the title of this episode, Hang On for Zeer Life. What the heck is a Zeer? Well, a Zeer, you're going to see in a second here coming up on the screen, a Zeer is a special type of refrigeration that was invented in Africa. Now, a Zeer works using the principle of evaporative cooling that Mackenzie mentioned earlier. And we're going to look at a Zeer pot in a lot more detail later because that's our activity for today. We're going to be building our very own Zeer pots. But as you can see on the screen here, essentially, for a Zeer pot, what you have is 2 clay or terracotta flower pots that you might see around. You probably have some in your garden, maybe. And inside, you have a smaller one, you've got a bigger one, and you fill it with sand so that it's really, really snug. You've got a small pot in the middle and a bigger pot on the outside. And those pictures showed a whole bunch of vegetables and fruits that were inside. Now, how this works is you fill it with sand, you pour water all throughout the sand so it gets really, really moist. It soaks up that water. And eventually, as air moves past the Zeer pot, that water that's inside the sand is going to start evaporating, okay? Sort of like how we sweat. And when that evaporates, it's going to collect on that inner pot and start to cool it down after a long period of time. So it's an example of evaporative cooling. Now, a pro of this Zeer pot design is sort of like the root cellar. It doesn't require us to put any energy into the system. It doesn't need to be plugged in or run on batteries or anything like that, like a modern day refrigerator. So we can just kind of leave it outside and let it do its thing, which is really, really cool. A con of it is that it only really works in certain climates. So the reason that it's more commonly used in places like the Middle East or in Africa is because they tend to have a lot of dry weather, really, really dry climates. And this principle of evaporative cooling works a lot better when the climate is really, really dry. So we wouldn't necessarily be using Zeer pots where we are filming the Couch Potato Lab here in Saskatchewan. You could, but it's not as common just because we don't have as dry and arid of a climate as a place like Africa or the Middle East.
Wow, thank you so much, Cole. I feel like I understand so much more about refrigerators and how they work, but I think Mackenzie has a quick graph to help us out.
Yeah, of course. So we were talking about different types of refrigerators, and they all had a little bit, they were kind of some differences. They looked different. Some of them had power sources, some of them different, but they all do have one thing in common. So I'm just going to graph this for you. So I just have a simple graph here with 2 axes. So I have time and temperature. So I'm going to start by graphing a food, so a food that's going to spoil over time with something that's just at room temperature. So we're going to say that yellow is room temperature. So if this is room temperature, I guess let's switch this, because I'll leave the temperature constant. I'll switch this to spoilage.
Ooh, spoilage.
Nice.
Spoilage, because I want to know how it's going to spoil. So we're going to say that the temperature is pretty constant. So this is at room temperature. So it's going to, over time, it's going to spoil pretty quick. But if we use something that is in refrigerators, refrigerator.
Nice.
Now, a refrigerator is typically kept at around 4 degrees Celsius. So 4 degrees Celsius, we'll say. So we'll say it's starting here at the same rate, but this spoilage is going to happen a lot slower. So if this is where we can no longer eat it, if that's the spoilage line that we can no longer eat, you can see that this one that was at room temperature got there a lot faster than this one. So that's kind of the concept of refrigeration, and that's how it helps with our food preservation as well.
Awesome. Thank you so much, Mackenzie. That helps me even grasp it that extra step. I'm really interested in that Zeer pot, though. I wonder if we could make our own.
I mean, if you want us to, we could probably figure out a way. I think, Mackenzie, you want to make a Zeer pot?
I think we should, for sure.
Let's do it.
All right. So luckily, we just happen to have all of the materials with us today.
What are the chances?
So we're going to start with 2 clay pots. So I have a bigger one here and then a smaller one here. So at the bottom we had little drainage holes, which is normal for these pots. So to get around that, we just put some duct tape or any type of tape on top to make sure that our sand doesn't sneak out through there. And yeah, you're just going to want to make sure that one of your pots is small enough to fit inside, because we're going to use that for our next step. So I'm going to start with my bigger pot here. And the first thing we're going to do is we're just going to go ahead and fill it with some sand just at the bottom, so we have a base layer of sand. So I'm going to go ahead and, luckily I finished my coffee already, so I can use my coffee cup here as my little scooper.
It's a very nice mug. I like it.
Of course. So I'm just going to go ahead, scoopy scoop.
Excellent.
And I'm just going to make sure I have enough of a layer so that my pot, when it sits in there, it's going to be level. So I want it to be nice and level there. So I'm going to add a little bit more sand because it doesn't look like it's sitting quite high enough yet.
Cole, did you get yours to be sitting level?
I'm working on it here. So yeah, you don't want to fill it up too much with sand. You want about an inch, maybe a little bit more of sand at the bottom. And you want to, like Mackenzie was saying, level it off so that when we put our smaller pot inside, it sits level-ish. How did you do, Mackenzie, over there?
Yeah, I think mine's looking pretty good. Mm-hmm. Now, I'm just thinking, I was reading about these, doing my research on them, and for it to work the best, the sand has to be moist, so we want it to be kind of wet. So I'm thinking that if I just add the water at the very end, then the sand at the bottom might not be wet enough, right? So I think what I'm going to do before I secure this pot in there really good, I think I'm going to add a little bit of water, just enough so it makes the sand wet, but not so it's like drowning in there. So just a teeny bit so that it's nice and moist. So here we go. I'm going to dump a little. Oh yeah, and you know the sand will absorb that. So that's what we're aiming for, making sure that we only add enough that the sand will absorb it.
Kind of gives it the consistency of mud a little bit,
Yeah.
which is nice. And this will actually help your smaller pot sit nicely inside. It'll kind of get stuck in there, which will help it sit straight.
Yes. Okay, so now that we've done that, I think what I'm going to do next is we're going to have to be a little bit careful with this spot. But there's all of this room here in between my big pot and my little pot. So I'm going to very carefully, I'm going to fill that up with sand. So I'm just going to go through and dump sand around there and make sure we don't get it in that little pot, because that's where we're going to be putting our food. So we don't want to mix our sand.
You don't want sandy cukes.
Oh,
I hate a sandy cuke. If I'm putting lots of cukes in here, we don't want sand in that smaller part.
Definitely not.
Pot.
What's your favorite fruit, both of you, that you'll put in here? Mackenzie, what's your favorite?
My favorite fruit?
Yeah.
My favorite fruit. You know what? This is interesting because I would say that it kind of changes based on seasons because in my opinion,
true.
certain fruits taste better at certain times of the year based
definitely.
on where their growing season is. But right now, current fave, strawberries.
Oh, true.
Yeah.
I think that'll have to be my favorite as well. My little brother and I love to just eat strawberries together. We cut them up, sit on the counter, and then eat them. I love strawberries. Excellent choice. Cole, I know you mentioned cukes earlier, but what's
yeah.
your favorite? Is it cucumbers?
Well, cukes do hold a special place in my heart. I do like those little baby cucumbers. But if I really was choosing my favorite, do vegetables count? Are those allowed?
Yeah, sure. Fruit or vegetable.
Well, I would have to go with the humble carrot then. There's nothing like a humble orange carrot. And that's why they call me old carrot eyes, because I've eaten so many carrots that I almost at this point have better than 20/20 vision. I got
X-ray
real
vision?
good vision. So as you can see right now, I'm just still filling this in. I am getting a little bit of sand inside my small. I might get some sandy cukes, but that's okay. We can always adjust that later.
You know what? I'm getting sand all over my table. So you know what? Tomato, tomato.
Yes. This might get a little bit messy at home, so maybe put a towel down before you start.
Yeah, that'd be a great call. Now, speaking of berries, do you want to know a fun fact about me?
Yes.
When I was younger, my first summer job ever was working at a berry farm.
No.
Really?
Yep, and my favorite thing to do was on my little snack break, I would go and pick the berries and eat them, and it was just the most delicious tasting berries you could ever imagine.
They would be just fresh right off the tree. Or bush?
Lots of them were on vines.
Oh.
I mean, strawberries were my favorite back then too, so
How do you grow strawberries? Or like what are they on?
they're like little vines on the ground, I
Wow.
would say.
Huh, that's so cool.
Yeah.
So Mackenzie, when we're filling in this tiny space in between the pots, we want it. How much room do we want to leave for the sand, like at the top? How much are we talking?
I think we pretty much want it level.
Okay.
I mean, we want a little bit of a ridge because we're going to need to add some water and we don't want it to overflow. So I'm going to leave about, I'd say, like a centimeter or two. And I'm actually really packing mine down as well. So I'm packing it down. I think mine's about good. So here we go. I'll show you all here. So you can see I have sand all the way around and I really packed it down. Now, similarly like we did to our first layer, I'm just going to go ahead and add a little bit of water. Now this water, it is a key ingredient in our Zeer pot. A very key ingredient because it is very important for the evaporative cooling process to take place. So speaking of evaporative cooling, should we let's dive into how this works and why it's working so well. So Cole's gonna perfect his design over there.
It might take a while. Let's just say that if I put cucumbers in here, it might be more sand than cukes at this point. So I'm going to have to perfect this, but that's okay. Mackenzie's going to give us a really good explanation of how these Zeer pots are actually going to work.
All right. So we're going to pretend that this is our Zeer pot, kind of like cut in half. So if we're looking at it from the top down, this is our Zeer pot. So this is our inside pot. This is our outside pot, and this will be our sand. So essentially what is happening here is, again, it's called evaporative cooling, and that's releasing temperature by evaporation. So we have that moist and wet sand in here. So the middle pot, the heat from it, so the hot air molecules, they're going to get pushed to the outside of the pot and get pushed into that sand. Now that sand, it's moist and wet. So then what's happening is we're going to have the H2O, there's going to be some diffusion within it, so it's going to be moving all around. And then as the sand warms up, that moisture from that sand is going to evaporate out, and it's going to bring that heat out with it. So what we're left with is cooler portion in the middle, and then the heat escaping from the outside. Now, in order for this to work, we need to keep our sand wet. So if you're going to use your Zeer long term, you're going to want to make sure that as soon as you see your sand kind of drying out, you're going to want to keep adding water so that it stays nice and cool. Now, if you look here at my Zeer pot, and I think Cole is going to be doing a similar thing.
Yes.
The reason that we use clay pots is because they have little pores in them that allow the water to seep through and evaporate out. So it's going to be really important that we're using like a clay or a terracotta pot. Now, Vanessa, where did where did this idea come from? Where did these clay pots and the Zeer come from?
Very excellent question, Mackenzie. While we adjust our Zeer pots and get everything perfect, we get to find out about where it came from, and the inventor is actually our STEM Spotlight today.
On today's STEM Spotlight, we want you to meet Mohammed Ba Abba. He invented the Zeer pot in the 1900s. He's a Nigerian teacher who comes from a pot-making family. He utilized his knowledge of pots and science and was able to develop a refrigerator for people all across Nigeria and beyond. He helped decrease the rate of unemployment in Nigeria by employing people who needed jobs. These people were in charge of creating clay, farming pot, and creating the Zeer itself. What incredible work, Mohammed. Thank you.
Thank goodness we have our Zeer pots. What would we do without them? If you have any questions throughout the show or would like to show us your Zeer pot, please feel free to text us at 306-570-1013 or tweet us using the hashtag CouchPotatoLab at EyesYouth on Twitter. At EyesYouth is also our handle on Instagram, Facebook, TikTok, and here on YouTube. All right, should we see our final products?
Yes, we are almost. I've finally figured out my Zeer pot. So yeah, like Mackenzie was saying, we can see because of the tiny little pores in these clay pots, we've got some water that you can see at the bottom of the pot. And I've tried my best. Let's see if I can go like this. I've tried to level it out. As you can see, I did get a lot of sand.
It happens.
There. Tons, but that's okay. I've got some water in there. We got moisture. And Mackenzie, we've got these towels. What are we going to do with these?
Yeah, so we have these towels, and they're going to kind of act as almost like our lid. So I'm actually going to put some water on my towel so it's damp. So I'm going to just, pour some water on it. So
it's moist. We don't want it soaking, right?
No, absolutely not. I might have been a little bit water friendly over here, but that's okay. I'm just going to soak it all up. I got a big towel here.
Good thing we have that towel.
Yeah, we're just keeping this towel moist again to help us with that evaporative cooling. And this is just going to kind of act as a barrier from the outside. So when we put stuff in, we're just going to drape that over our Zeer pot just to keep that cool air in and make sure that it's working as good as it can. Now, Cole, yours is looking pretty good. How confident are you in it?
I'm pretty confident. I'm so confident, actually. I'm going to put a bagel inside there.
Oh, my goodness.
Cool it down.
For tomorrow's breakfast.
That's right. Keeping it cool. And I'm going to put my moist towelette over top of our Zeer pot. Am I doing this right, Mackenzie? This is how we want it, right?
You got it.
Yeah,
yes.
Perfect.
So our Zeer pot is ready for use. So we can go ahead and put some things in it. And maybe I would try, if I was going to test this out, I think that my scientific opinion would be that I might maybe put something in there and then I would put it out in the sun. And then in a couple hours, I would see if the air outside feels warmer than the air inside my Zeer pot. And if it's cooler, then I guess we know that it worked. But Cole was mentioning before that Zeer pots, they don't work super efficiently in all environments. And we've talked a lot about evaporative cooling and how this works for our Zeer pots, but there's also something called relative humidity that also affects how well our Zeer pots work. So relative humidity, it's actually a measure of water vapor. So it's the amount of water vapor present, and it's expressed as a percentage usually, and it talks about the amount needed for saturation in the air. So very basically, it's talking about how much moisture is in the air for it to create a water droplet. So rather than the moisture existing in like a gas form, how much needs to exist in the air for it to exist as a liquid. So in Regina today, I looked on the weather report. I'm not sure if you were able to listen to that or not today, but the relative humidity outside in Regina today is 56%. And these percentages are very unique to each area, and they do change day to day, year to year, season to season. So typically these Zeer pots work the absolute best at 0% humidity, because as I was talking about in that root cellar, when it has a low humidity, it's constantly looking for areas that have moisture to take the moisture out and bring that into the air. So they're kind of like stealing the moisture there. So you can see that arrow there, that's bringing the moisture out and evaporating it out. So typically these Zeer pots work best in really dry areas that have a very low humidity, so places like deserts or really hot places that are hot year-round, like places like Africa and things like that. Now humidity, it's used a lot, and we keep our houses at a specific humidity so that they're comfortable for us. So one way to tell if your house has too much humidity is if you look, maybe if you're cooking or it's really hot outside, if you look on your windowsills and there's like liquid around your windowsills, that means that your house is very humid. So that might happen on a very hot summer day here in Regina. Or sometimes if you go outside and it's really humid outside, you can kind of feel like there's like moisture on your skin, or maybe your hair will get really curly. So that's a sign that we have high humidity. Now I did a little experiment here. So very simply, I just added some beaker in a cup. Now if we zoom in really close here, we can actually see that there's water droplets that formed all the way around this beaker. Now that's a good way to test to see if your humidity is too low, because if the humidity were really low in this room, these water droplets wouldn't have formed as much, because as the ice melts, because melting is a relatively slow process, that air would have escaped from the outside of here and it would have been absorbed by the air and atmosphere to try to make up for that dryness in the air. But because they formed as water droplets, we know that the humidity in here isn't too low and that we have a good humidity level.
Excellent. Thank you, Mackenzie. And before we get into how we're going to test stuff, we have a quick question from the Hayes brothers. This is just for Cole. I think it's a nice, fun little quick science break. We can get a nice backstory on Cole. So Mackenzie mentioned her first job at a berry farm. Cole, what was your first job?
Wow. I'm so glad that you asked, Hayes brothers. My first job, I worked at a restaurant. I was a dishwasher, and trust me, I was like a wizard back there, grabbing the hose, plates coming in, whoosh. And you know what? It was quite the opposite of cooling back there. It got very, very hot in the kitchen because there was like lots of steam coming off from when I was washing the dishes and stuff like that. It was a quite the interesting experience. I actually one time some of the cooks threw hash browns at me.
What?
And I don't know if that was a joke. Like they were saying, hey, you're one of us now. You can join our crew. Or if they were just throwing hash browns at me because they thought it was funny. But regardless, that was my first job. I was a dishwasher at a restaurant. Not quite as glamorous as working on a berry farm. But you know what? Yeah, you'll learn something through an experience like that. I'll tell you that much.
Very true.
Yeah.
Thank you, Cole. And now we know all about your backstory. I feel like we're best friends now. I have to take Potato spot as your best friend. So Cole has an interesting way of showing us how we're going to know what temperature things are, what might be going on, some special things that we get to learn from our friend that we know very well now, our friend Cole. What do we have?
Well, so I've moved my Zeer pot out of the way. I'm letting that bagel chill, trying to get that sucker down to a nice, -2 maybe. That's what I like to eat my bagels slightly frozen. All right. So we've built these Zeer pots, and Mackenzie has talked about how they use evaporative cooling to cool things down, but how do we actually measure whether things are cold or whether things are hot? Well, we use something called temperature. Now, temperature you've probably heard of, but the actual definition of temperature is just the intensity of heat given to on an object or on a substance. Okay, so we measure temperature in a few different ways. Here in Canada, where we're filming the Couch Potato Lab, and a lot of other countries across the world too, we use degrees Celsius. So I don't know, Mackenzie, did you notice what I don't think she did notice, but when she was checking the humidity today on the weather report, she might have also noticed that the temperature out. And I think I'm going to guess the temperature was probably 27 degrees Celsius today.
It actually was when I looked. It's like 26, 27 right now. That's a really good guess.
Thanks. Not bad, hey? So temperature we can measure it in Celsius, but in a place like the United States, they actually use Fahrenheit, which is, again, we're still measuring temperature, but we're just using a different scale to do so. Now, when we measure temperature, we use a device called a thermometer most often to actually measure that temperature. And really quickly, I'm going to teach you how you can build a really cool, simple thermometer at home. So what I have here is just an old plastic water bottle, and at the bottom, I just have a little bit of water, okay? So I think it's about a quarter cup of water in there. the next thing that we're going to do is we are going to add a 1/4 cup of rubbing alcohol. All right. So this is a really, really common thing that you might use to put on like cuts and stuff to disinfect. But we're going to put this rubbing alcohol about a 1/4 cup. Okay. Which I'm just eyeballing here is like that much, let's say. Okay. And we're going to pour this into the water that's in our water bottle. Pour that in here. You'll notice that I have some green stuff on the top of this. You're going to see what that is later. Now, when we're using rubbing alcohol, it's something that we do need to be careful of. We definitely don't want to get it in our eyes or in our mouth or anything like that. So we just have to be careful and maybe have an adult around while we're doing this as well. So inside our water bottle, we have a mixture of water and rubbing alcohol. And you notice from where you are viewing at home, you probably can't tell the difference between what's the water and what's the rubbing alcohol because they're both colorless liquids. So they sort of mix together. But up close, I can kind of see there's some weird waves going on in there. And that's caused by the rubbing alcohol and the water actually not mixing together. But the next thing that we're going to do is we're going to add some food coloring. Now I'm using green because green is my favorite color, obviously. And you can use any color that you want at home. I'm going to add a few drops of green food coloring. And really what this does is, first of all, it makes it a heck of a lot more fun, but it also helps us see what's going on in our thermometer. So I'm adding a few drops. I'm going to take the cap, make sure it's on there snug and tight, and I'm just going to give it a little bit of a shake to mix that all up. And now we have this lovely green concoction inside of our water bottle. Okay, now comes the fun part. What you're going to do is, from your mixture that you've created in here, you're just going to pour like a tiny, tiny bit out into a different container. I'm just going to use this measuring cup from before. Like a few little drops, a little pour is good enough. Just you don't want it to be too much, but that's about enough. I think it equals out to about 2 tablespoons if you want to be really precise. So you pour a little bit out, and next you're going to take a straw, an ordinary straw, and it tends to work a lot better if you use a thinner straw. You can get really wide ones, but the thinner ones work better. So what you want to do is you're going to put the straw inside the bottle, but you want it inside the liquid at the bottom, but you don't want it touching the bottom of the water bottle. So that's really important. This straw actually isn't even long enough to touch the bottom, but if you have a longer straw, you want to make sure that the straw, when it's in there, isn't actually touching the bottom of the water bottle. So what you're going to do is to secure it in place, if you grab some Play-Doh or some modeling clay like I have here, you're going to wrap it around the top of the water bottle and the straw so that it holds the straw sort of in place where we want it. So this is the part where I'm not so great at because I don't have very deft hands here. But we're just going to sort of secure this. I'm going to stick this to this so that it holds in there.
You're doing so great, Cole.
Mackenzie, I really, really appreciate that because I'm kind of nervous. Okay.
Oh, don't be nervous.
I love how your modeling clay matches your water.
Thanks.
Looks very, very good. I'd put that in my kitchen. Oh, yeah. Looks great.
So the straw is almost secured here. There we go. So we've got a nice tight seal. And if you can see, it might be a little bit hard, but again, the straw is inside the liquid. It's dipped inside the liquid, but it's actually not touching the bottom of the water bottle. And again, that's an important piece there. So you just want the straw slightly submerged, but not all the way in. Okay, now comes the tricky part. And I don't actually have exactly the proper tools to do this. So I'm going to be being very, very careful. But what you want to do now is with that rubbing alcohol and water mixture that you took out of the water bottle from before, you're going to pour it back down the straw, okay? Now, because the mouth of the straw is so tiny, it would be best if you had like a dropper and you dropped it in. I don't have a dropper and I have a funnel, but it's too big. So we're gonna just really, really be careful. And if I spill a little bit, that's okay. But you wanna just try to get as much of that in there as possible. So I'm gonna be very careful and pour some of this back inside.
You got it.
Oh, I think I'm doing pretty well.
Yeah, I don't see anything spilling.
Holy moly.
Doing great.
There we go. Okay, so it's in there. Now, you might not be seeing anything at home, but that's okay. What's actually going to happen is this. Now that we've poured some of that liquid down inside of our straw, you want to be really, really careful. And again, remember that it's actually open at the top. The straw is open, so don't like tip it upside down or anything like that. But how this thermometer is going to work is the liquid inside is going to expand or compress depending on the temperature. So the liquid inside the straw that we poured down there, if the temperature gets really, really high, let's say we put this outside, out on the deck today, where it's really, really hot, 27 degrees we said, the liquid that you'll notice will start crawling up the straw. And if we take it back inside, the liquid will go down. Now, the reason that this happens is because when liquids are heated up, they start to expand. So the alcohol water mixture inside is going to start expanding and crawling up the tube when it gets hot. And the opposite will happen when it gets cold. So this is our very own like homemade DIY thermometer. But the cool thing is a thermometer like this one works exactly the same way. So this type of thermometer, which I think is used for cooking, is it has the exact same principle. So most thermometers that we would see to measure food or to measure the temperature outside, they have one or two things in them. They either have some sort of alcohol liquid or they have a liquid metal called mercury, all right? And again, the same principle applies as our water bottle thermometer. When those liquids get hot, they start to expand and they will push up the tube, and that way you can read the temperature. So as the liquid expands, it might get to, let's say, 80 degrees. And then we know that the temperature that we're measuring of this boiling water or whatever it is 100 degrees or 90 degrees. So thermometers all kind of work in the same principle. I have another one here. Again, it's all working on the same sort of principle of expanding and compressing liquids. So you can make your own thermometer at home and you can try it out on a hot day.
Wow, that was really good. Thank you, Cole. I feel like I could just go build any thermometer, test the temperature of anything.
So speaking of thermometers, I'm actually going to use a thermometer to explain something called heat capacity. Now, heat capacity is the amount of energy needed to raise a substance by 1 degree. So before I talk about how this affects our Zeer, I'm going to do a little explanation of things over here. So I've been boiling over here some milk and some water. So we're going to test their temperature because they're both boiling right now. So don't try this at home. This is an adults only experiment, but we're going to demo it here for you. So we're going to compare their heat capacities by looking at their boiling point. So we're going to see at what temperature each of these is boiling at. So I'm going to go ahead and use my thermometer and test the water first. So just like Cole mentioned, it's going all the way, that mercury in there is raising up. So it's pretty hard to see. I'm not sure if you can see this on camera, but
Well, I think you can.
yeah,
I see that red line.
There you go.
yeah, it's raising up. So it looks like we're at, it's still rising. I'll give it a few more seconds here. 1, 2, 3. And I'm going to go ahead and pull that out. And it looks like that red, I'm not sure if you can see it, but it's right around, it's dropping rapidly here, but it was right around that 95 to 100. And you know what? That works with the scientific boiling point of water. They say that the scientific boiling point of water is right around 100 degrees Celsius. So now I'm going to go ahead and measure my milk here. All right, here we go. It's rising up. Now my milk was being a little bit stubborn. It was not wanting to stay in my beaker, so I had to turn it off. And now it's rising a lot. Yeah, so this one looks like it's around like 150-ish.
Whoa.
So that means that it has a higher boiling point, and that has all to do with the heat capacity. Now it's hard to find like a specific temperature of the boiling point for milk because it actually depends on the different milk, like the percentage of fat and things like that in it. There's many different types of milk and percentages of milk, but now we know that they do have very different heat capacities. Now, in terms of our Zeer, some things we might want to look at in terms of heat capacity is we moistened our sand with water. And now, if you use something with a different heat capacity, such as something like, rubbing alcohol, or maybe something like oil, the heat capacity is different, so it takes a different amount of energy to heat it up, and that also affects the evaporation process in turn. So, another experiment you could do with the Zeer you already built would be for a couple days, you could moisten the sand with water, and see what the temperature is like inside, if it's working well, not working well. And then maybe for a few days you could moisten it with something else, maybe like some rubbing alcohol, different things like that, and just try to test out some different substances and different liquids that have different heat capacities and see what it does to the evaporation process and how it affects the evaporative cooling of our Zeer.
Wonderful. Thank you so much for explaining the specific heat capacity and all the science behind that, Mackenzie. That's really excellent and very needed for our science showdown. That's there we go. Awesome. So, for our science showdown today, I'm going to be giving, for both of you, you're going head to head. It's Cole versus Mackenzie today. I'm going to be giving you a situation. And we're going to have two different substances that are going to be part of our situation, and you're going to have to tell me which one you think has the higher heat capacity and which one you think has the lower heat capacity. So we can take Mackenzie's principles that she taught us and apply that to these situations. Are we ready for our first situation?
I'm ready.
I got it.
Ready. Yeah.
Okay.
So what do we do when we know the answer? Because I'm
So
feeling
true.
very confident. I think I'm going to know all the answers, so I just want to know.
Let's make an animal sound.
An animal
Sure.
sound? You
Yeah,
got it.
Okay. So when you think you know the answer, give us an animal sound.
Mm-hmm.
All right.
All right.
Situation 1. You get to the beach. You kick off your shoes, and it's so hot on the sand. Uh-oh, what are you going to do? You're going to run to the water, and the water is immediately cooling. So the water's much colder than the sand, and the sand's very hot. And it's just from the sun this morning. It's only warming up from the sun. Which one do you think has a higher heat capacity? Water or sand? Oh,
Whoa.
Mackenzie was ready.
What was that?
It's a pig. It's
Oh.
a pig oinking.
Ugh.
Yeah, okay. Anyways, I'm very good at my sound effects. It's what I'm known for, actually.
Yeah.
Anyways, I think that the water must have a higher heat capacity because my reasoning is that it would have taken more energy from the sun to heat it up. So that's why that little bit of energy heated up the sand, but not the water. Am I right?
You're totally correct. So the specific heat capacity of water is 4,187 joules per kilogram Celsius, and sand is only 780. So you totally are right. That's why that happens. It's because the sand doesn't need as much energy to make it hot. Situation 2, are we ready?
Yes.
You got it.
Yes.
Okay, here's the situation. You are a candle maker, and you also have a young baby sister that you're babysitting at the same time. So you have two tasks going on, baby sister and your candle business. Your stove has 2 burners, much like our hot plate that Mackenzie was using earlier. So you have 2 burners, and each burner will be utilized. On the first burner, in a pot, you will be preparing your sister's bottle with milk in it. We've seen that already. You'll be preparing your sister's milk on the first burner. In the second burner, on that pot, it will be some paraffin wax. Okay, so we've got it going. We've got milk in one for your sister's bottle and wax for your candle in the other. They're both melting, same temperature settings, and the wax ends up being ready sooner.
Moo.
Yes, Cole.
Moo, moo,
Quack,
moo.
quack, quack.
Moo, 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 moo. How did you know, Vanessa, that I had a baby sister and I'm also I'm a hobbyist of sorts, and I do
Wow.
like to make candles in my spare time. So I should know this exact answer. The answer to which between milk and wax has the higher heat capacity is milk.
Yes, absolutely correct. That's totally awesome. Good job.
Thank you.
Milk's heat capacity is 3,930 joules per kilogram Celsius, and then wax is it's still a lot, but 2,200. So good job. This
Yes.
is the tiebreaker. Situation
Oh, boy.
3
Okay, here we
will
go.
bring us
Here we
home.
go.
I'm ready.
Okay, situation 3. We're planning to go on a hike with your family this weekend. You can't decide if you want to bring your plastic water bottle or your glass water bottle along. You don't know which one. You love having cold water, so you decide to perform an experiment before you go, because you got time. It's the trip's on the weekend. Okay, you fill each bottle with water and leave them outside in the sun for 30 minutes. When you return, the glass water bottle is hotter than the plastic water bottle.
Whoa. Quack, 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 quack.
Yes, Mackenzie?
I don't have it.
Go ahead.
I'm going to go with the plastic must have a higher heat capacity because it was colder.
Absolutely, that's completely correct.
She's
I
brilliant.
win.
She's brilliant.
Mackenzie wins. You get a special prize of,
What is it?
yeah, you're
Mackenzie,
just doing
I
great.
will give you a prize.
A bagel?
I will give you the bagel that I've been cooling. in my
Oh,
Zeer.
good idea,
Yes.
Cole. I didn't think of a surprise for Mackenzie earlier, but I know that Cole's got my back. So now it's time for our favorite segment after that amazing science showdown of Ask Our Scientist. Okay, our first question comes from Jonathan. Thank you for your question, Jonathan. And it is, what's freezer burn?
Ooh.
I got this one.
Okay, Mackenzie, you take
Go
this.
ahead,
You
our
take
winner.
this.
Yeah, so as we were talking about before, there can be some water molecules that escape from our food through evaporation. But as those water molecules kind of head out, sometimes oxygen molecules can seep in. And when those oxygen molecules kind of seep into our food, they can kind of change the taste or the texture of our food. So although it is still safe to eat that food, it might just taste a little bit off. So yeah, it kind of dries out our food and makes it taste a little bit different. So it causes those really dry spots in our food by oxygen molecules seeping in.
Okay, thank you. Our next question comes from Eli. Thank you for your question. And his question is, why are the bottoms of some refrigerators warm or hot, but inside the refrigerator is cold? Why is that?
Well, Eli, thank you for the lovely question. Now, Vanessa was talking earlier about how these modern refrigerators work. And one of the things that she mentioned is inside there's this chemical, this substance called a refrigerant. All right. And that is the real workhorse of the refrigerator that's doing all of the cooling. So if you've ever put your hand, I know I lose things underneath the refrigerator all the time. And when I try to put my scrawny little arm underneath there to grab, I don't know, I like to play with buttons and things like that. I can never get them. But one thing I do notice is it's very, very warm down there. And so you're right. You might feel some warmth underneath the refrigerator. Now, the reason that is because underneath the refrigerator, what you are putting your hand near when you feel that warmth is something called the condenser coil. Now, the condenser coil is the refrigerant is going to run through that, and this is where the heat is actually removed from your refrigerator. So the reason it feels warm down there is because the refrigerator, again, we want to keep things cold in there. So what it's going to do is start pumping out the heat and blowing it out to the bottom of the refrigerator. So we don't want that heat to stay trapped inside the refrigerant and stay inside the refrigerator, because otherwise our refrigerator wouldn't be doing a very good job of keeping things cold. So down at the bottom of the refrigerator is where that heat is going to be sort of blown away from the refrigerator.
Thank you, Cole. Our last question comes to us from Hannah. Thank you for your question. And it is, which places in the world would reach 100% relative humidity? Mackenzie, I know you're the humidity expert.
Yeah, you got it. So a lot of the most humid places in the world are really close to that equator. So places where it's warm all year round, because their temperature isn't affected as much by the tilted axis of the Earth. So lots of places in South and Southeast Asia are among the most humid. So places like Jakarta in Indonesia and Singapore, those places are very humid because they stay warm all year round. And they're also very close to large bodies of water, and they experience a lot of overcast weather. So all of those things relative to each other help keep the air very moist, so it keeps it very, very humid there. Wow. So in those cases, you might not want to make a Zeer there because it might not work well because, again, these things work best with low humidity levels.
Thank you, Mackenzie. Thank you for all your questions and for watching. And thank you to our supporters, Actua and the University of Regina. And have a great rest of your day. Bye.
Bye.